Imagine this. You press your palm against a sun-warmed stone, solid, real, unmistakable. You breathe in crisp mountain air, smell pine, feel gravity anchor you to the earth. Everything screams, this is real. But what if every sensation, every atom, every color, every heartbeat was not the foundation of reality, but a shadow, a projection, a cosmic mirage painted not with matter, but with information? And what if the true universe, the real one, lives not here in 3 dimensions of space, but on a distant, invisible surface, like a movie playing on a screen so vast we're inside the story, unaware of the projector? This isn't science fiction. It's a radical idea born from the deepest puzzles of modern physics. Black holes that vanish, entropy that refuses to vanish with them, and a startling discovery. The maximum amount of information any region of space can hold doesn't grow with its volume. It grows with its surface area. Think about that for a moment. Your room, say 10 feet by 10 feet by 10 feet, contains 1,000 cubic feet of space. Common sense says the more space, the more stuff you can store, books, memories, even secrets. But physics whispers something unsettling. If you tried to pack that room with information beyond a certain limit, it wouldn't overflow like a closet. It would collapse into a black hole. And the exact moment that happens, the moment reality breaks, depends not on how much space you have inside, but on the size of the walls surrounding it. That's the first tremor of the holographic principle. It suggests our 3-dimensional world might be a kind of illusion, a vivid, immersive simulation projected from a 2-dimensional reality at its boundary. Now, don't mistake this for mysticism. This idea didn't come from dreamers gazing at stars. It emerged from cold, hard, math blackboard equations scrawled by physicists wrestling with the fate of information swallowed by black holes. And it has survived decades of scrutiny because, strangely, it works. To understand how we got here, we must journey back, not to ancient myths, but to the edge of a black hole where space, time, and information collide in ways that defy everything we thought we knew. But before that, let's ground ourselves in something more familiar, something that feels unquestionably real: your own body. Every cell, every thought, every memory encoded in patterns of atoms. But atoms themselves are mostly empty space. And those particles? They're not tiny billiard balls. They're excitations, ripples in invisible fields that stretch across the cosmos. Even the solidity of matter is a persistent illusion created by forces too small to see. So if matter isn't solid, if space isn't empty, what is? Real? Perhaps the answer isn't stuff. Perhaps the answer is data. In the quiet hum of the quantum vacuum, in the flicker of virtual particles popping in and out of existence, physicists began to suspect that the universe might be, at its core, a vast information processor. And just like a video game renders a 3-dimensional world from 2-dimensional code, our cosmos might be rendering reality from a lower dimensional script written at its edge. This is the holographic universe, not a metaphor, not a guess, a framework that may hold the key to unifying quantum mechanics and gravity, the 2 great pillars of physics that, for a century, have refused to speak the same language. In the next act, we'll stand at the event horizon of a black hole, the place where the holographic idea was born, where Stephen Hawking's paradox nearly broke physics, and where a deeper truth began to shimmer into view. But for now, just ask yourself, if reality is a projection, who or what is watching? There is a place in the cosmos where gravity wins, not just wins, devours, a point so dense, so warped, that not even light can escape its pull. We call it a black hole. For decades, it was the ultimate tomb, silent, featureless, final. until it started whispering. In the early 1970s, a young physicist named Stephen Hawking did something astonishing. He applied quantum theory, the rules of the very small, to the edge of a black hole, that invisible boundary called the event horizon, and what he found shattered the classical picture. Black holes, he realized, aren't completely black. They glow faintly, with a ghostly heat now called Hawking radiation. This alone was revolutionary. But then came the paradox. If a black hole radiates energy, it must lose mass. Over eons, trillions upon trillions of years, it will shrink and vanish. But what happens to everything that fell in? A star, a planet, a diary, a life. All that information encoded in the positions, spins, and quantum states of particles was thought to be trapped forever. Now, if the black hole disappears, where does that information go? Here's why this matters. In quantum mechanics, information is sacred. It can't be created or destroyed. You can scramble it, hide it, encrypt it, but it must always be recoverable in principle. It's like burning a book. The ashes seem random, but if you knew the exact motion of every molecule, you could, theoretically, reconstruct every word. But black holes appear to violate this law. They seemed to erase the past, and that threatened to unravel the very foundations of physics. For years, physicists were divided. Some said information truly vanished, meaning quantum mechanics was incomplete. Others insisted it had to escape, somehow woven into the Hawking radiation. But how? The radiation looked random, thermal like the hiss of static, no hidden messages, no patterns. Then, in the mid-1990s, a breakthrough came, not from telescopes, but from string theory. A physicist named Juan Maldacena proposed something so bold it redefined the problem entirely. He showed that a certain type of black hole, living in a universe with 5 dimensions and a negative curvature, a space called anti-de Sitter space, could be perfectly described by a quantum theory that lived only on its boundary, a 4-dimensional surface with no gravity at all. In other words, the black hole's interior, the drama of falling matter, warped space, and quantum chaos, was mathematically identical to a hot, turbulent soup of particles dancing on a distant screen. No gravity needed there, just quantum fields interacting. This was the first concrete realization of the holographic principle. Reality inside was encoded on the outside. The black hole wasn't destroying information, it was storing it, encrypted on its surface. And as it evaporated, that data slowly leaked out through the Hawking. Radiation, not as noise, but as subtle correlations, like a symphony hidden in static, audible only to those who knew how to listen. Think of it like this: you drop a photograph into a shredder, the pieces scatter. To your eyes, it's gone. But someone with the right algorithm, knowing exactly how the blades cut, could reassemble every pixel. The black hole is that shredder, and the universe has the algorithm. This insight transformed black holes from information destroyers into the universe's most efficient hard drives. In fact, they hold more information per square inch than any known object. A black hole the size of a sugar cube could, in theory, store more data than all the books ever written. Not because of its volume, but because of its surface area. And that's the key. Jacob Bekenstein, long before Hawking's radiation, had already hinted at this. He noticed that when matter falls into a black hole, its entropy, the measure of hidden information, increases, but not in proportion to its volume, only to the area of its event horizon. Double the radius, the surface area grows by a factor of 4, and so does the entropy, volume. That grows by a factor of 8. But entropy ignores it. Why would the universe care about surface, not space? Unless space itself is secondary. Imagine a library where every book's contents are printed not on its pages, but on its spine. The thicker the book, the more pages it could hold, but the real information is only on the outside. Open it and you see words. But those words are just echoes of what's already written on the cover. That's the black hole's secret, and perhaps the universe's. Just about exotic objects light years away. If black holes obey the holographic rule, why wouldn't everything else? Could empty space, even the vacuum around you, operate under the same principle? That question leads us beyond the event horizon into the very fabric of space-time, where we'll discover that the cosmos might not be built from particles or forces, but from bits, and that the true stage of reality isn't three-dimensional space, but a vast, invisible screen at the edge of everything. But before we get there, let's ask, if the universe is a hologram, what is it projected from? And where is that screen? That's the mystery we'll unravel next. Close your eyes. Imagine the entire cosmos, not as stars and galaxies floating in void, but as a single intricate pattern, not painted in light or matter, but in relationships, in connections, in data. This is the vision emerging from decades of theoretical struggle, that space-time itself is not fundamental, it's emergent. Like temperature emerges from the motion of atoms, space and time may emerge from something deeper, something more primitive, and that something is information. The clue came not from telescopes, but from the mathematics of quantum entanglement, a phenomenon Einstein once called spooky action at a distance. When two particles become entangled, their fates are linked no matter how far apart they drift. Measure one, and you instantly know the state of the other. Not because signals race between them, nothing moves faster than light, but because they share a single quantum description. For years, entanglement seemed like a curiosity, a quirk of the quantum world. But then physicists began to notice something strange. The more entangled two regions of space are, the more connected they become geometrically. In certain models, if you reduce entanglement between two patches of space, a wormhole, a tunnel through space-time pinches off and disappears. If you increase it, the tunnel widens. It was as if entanglement were weaving the very fabric of space. This led to a startling idea. Space-time is held together by quantum threads of information. Cut enough threads and space tears. Weave them densely and distance collapses. The geometry of the universe, its hills and valleys, its curvature near massive stars is not carved in stone. It's written in code. And that code lives not in the volume, but on the boundary. Enter the ADS-CFT correspondence, the mathematical jewel discovered by Juan Maldacena in 1997. It's not just a metaphor, it's an exact duality. On one side, a five-dimensional universe filled with gravity, strings, and black. Holes called anti-de Sitter space, or ADS. On the other, a four-dimensional quantum field theory without gravity, known as a conformal field theory, or CFT, living on the boundary of that space. Every event inside the five-dimensional bulk, every collision, every ripple of space-time has a perfect counterpart in the four-dimensional quantum dance on the edge. No loss, no distortion, just a change of language. It's like describing a storm. One poet writes of thunder, wind, and rain. Another writes of pressure gradients, humidity, and jet streams. Same storm. Two vocabularies. But here, one vocabulary includes gravity, the other doesn't. Why does this matter for our universe? After all, we don't live in anti-de Sitter space. Our cosmos is expanding, flat on large scales, and filled with dark energy, more like Sitter space, true. But ADS-CFT is the only full working example we have of a holographic universe. It's a laboratory in the mind, a mathematical universe where we can test how information on a surface builds a volume with gravity. And in that lab, something extraordinary happens. The interior, the world of reality we'd experience if we lived inside, doesn't exist independently. It's a reconstruction, a decoding, like listening to a symphony and inferring the shape of the concert hall from the echoes. The bulk is not primary, it's derivative. Think of a 3D hologram on a credit card. Tilt it and a bird seems to flap its wings. But there's no bird inside the plastic, only a flat surface etched with interference patterns. The depth, the motion, the illusion of life all emerge from 2 dimensions. Now scale that up, not to a bird, but to a galaxy, to space-time itself. In the holographic view, the Big Bang wasn't the explosion of matter into void. It was the moment a vast, entangled quantum system on a lower dimensional surface began to decode itself into geometry. Time, space, gravity, all crystallized from information relationships. This flips our intuition on its head. We've always thought that to describe a region of space, you need to specify what's inside it. Fields, particles, energy densities. But the holographic principle says none. All you need is the state of the boundary. The interior is redundant, like a dream generated from a few lines of code. And here's the most unsettling implication. If the boundary contains all the information, then nothing inside is truly local. That coffee cup on your desk, its existence isn't just here. It's a projection of correlations spread across the cosmic horizon. Every atom is entangled with the edge of the observable universe. We are not separate from the cosmos. We are its echo. But where is this boundary? In ADS space, it's mathematically well defined, like the walls of a room that curves back on itself. But in our expanding universe, the boundary may lie infinitely far in the future, or in the deep past, or perhaps on the cosmological horizon. The farthest light could have traveled since the Big Bang. We don't yet have a complete holographic description of our universe, but the signs are mounting. Gravitational waves from colliding black holes match predictions from boundary quantum models. The entropy of the observable universe, its total hidden information, is suspiciously close to the area of the cosmic horizon, not its volume. Coincidence or a clue? What we're glimpsing is a new kind of cosmic blueprint, not drawn in forces or particles, but in bits, entanglement, and symmetry. And if this blueprint is real, then the universe isn't just like a computer. It is a computation, not in the sense of silicon, chips and software, but as a natural process where information evolves according to physical law, and in doing so, manifests as space, time, and matter. This doesn't mean we're in a simulation run by aliens or future humans. That's a different idea. 1. Rooted in technology. The holographic principle is deeper. It suggests that reality itself, by its very nature, is informational at the core, even if no one is running it. So if space-time is woven from quantum data, how does that data build the world we see? How do pixels of information become planets, stars, and the breath in your lungs? That's the alchemy we'll explore next, where the abstract meets the tangible and the universe learns to render itself. Imagine you're standing on a beach at night. Above you, the Milky Way spills across the sky like powdered silver. Beneath your feet, grains of sand shift with each wave. Everything feels continuous, smooth, flowing, infinite in detail. But we know better. Zoom. In far enough, and the sand breaks into individual crystals. Zoom further, and those dissolve into atoms. Then electrons, quarks, fleeting quantum fields. Now go one step deeper, not into smaller pieces, but into the rules that bind them. What if, at the most fundamental level, the universe isn't made of things at all, but of questions and answers? Yes or no, on or off, 1 or 0. This is the radical proposal of the holographic universe. Reality is built from informational pixels, not scattered through space, but painted on its boundary. Each pixel isn't a dot of matter. It's a unit of quantum information, a qubit, capable of holding more than just 0 or 1, thanks to superposition and entanglement. And here's the miracle: when these boundary qubits interact in just the right way, they don't just describe space, they create it. Think of a video game. When you walk through a forest, trees don't exist as solid objects in your computer's memory. They're rendered on demand, based on your position, the light, the code. The game world is an illusion generated from underlying data. Now imagine a game so advanced that the characters inside it believe the forest is real. They feel bark, smell moss, argue about whether the trees existed before they arrived. That's us. But unlike a video game, the holographic universe isn't rendered by a CPU. It renders itself through the laws of quantum mechanics playing out on the boundary. How does this work? Let's return to entanglement, the cosmic glue. In the boundary theory, regions that are highly entangled correspond to nearby points in the bulk, the interior spacetime. Low entanglement, those points are far apart. No entanglement, they might as well be in different universes. In other words, distance isn't primary. It's a measure of how much quantum information two places share. This flips geometry inside out. Instead of saying these two stars are 10 light years apart, so they can't influence each other quickly, we say, these two stars appear 10 light years apart because their underlying boundary data is only weakly entangled. Space is not a container, it's a network of correlations. And time. Time may emerge the same way. In the boundary description, there is no ticking clock, just a timeless quantum state like a frozen block of code. But as entanglement spreads, as information scrambles and reorganizes, a direction emerges, a before and after. A before and after. Cause and effect. This is entropy in action, not as disorder, but as growing complexity of quantum relationships. The arrow of time may simply be the universe learning more about itself. Now, how do particles arise in this picture? They don't live in space. They are disturbances, ripples in the entangled web. Like plucking a guitar string made of information, the vibration travels not through a medium, but through the pattern of correlations. An electron isn't a tiny ball, it's a persistent knot of data. That behaves like a particle when probed. A photon, a wave of shared information moving across the network. Even gravity, Einstein's curvature of space-time, may be a thermodynamic effect. Like pressure emerging from molecular motion, gravity could arise from the way information on the boundary responds to changes in entanglement. This is the essence of the entanglement geometry idea. No strings, no loops, just quantum information weaving the stage on which physics plays out. But if everything is information, why does it feel so solid? Because the code is incredibly dense. At the Planck scale, the smallest meaningful length in physics, about 100 million billionths of a meter, the universe's pixel size is so fine that smoothness is an excellent illusion. It's like watching a movie on a high-resolution screen. From a distance, the image is seamless. Only when you press your nose against the glass do you see the grid. We live far from the Planck scale, so space feels continuous, time feels linear, Matter feels substantial. But peel back the layers and you find a cosmic loom weaving reality from threads of data. Consider a single hydrogen atom, one proton, one electron. In the standard view, it's a tiny solar system held by electric force. In the holographic view, it's a pattern of boundary entanglement so stable, so self-reinforcing that it persists across time and mimics a particle. Scale that up, multiply by 10 to the power of 80 atoms in the observable universe, and you get galaxies, stars, oceans, and the neural sparks that let you read these words. All of it echoed from a surface. This doesn't diminish reality. If anything, it makes it more astonishing. A sunset isn't less beautiful because photons are excitations of a quantum field. A symphony isn't less moving because it's air vibrations. The holographic universe isn't less real because it's informational. It's more profound because it means that everything, every supernova, every silent thought is part of a single unified code. Not written in stone, but in relationships. Not carved in space, but projected from its edge. But this raises a haunting question: if the universe is rendered from a boundary, where is that screen? Is it surrounding us like a bubble? Is it in the distant future? Or is it something we can never see by design? That's the mystery of the cosmic screen, and it's far stranger than any mirror. You've seen holograms before: a security sticker on a credit card, a shimmering display at a museum. Tilt it, and depth appears where there was only flatness. But those holograms have one thing in common: you stand outside them. You see the projection from the front. The screen is obvious: the plastic, the glass, the film. Now imagine a hologram where you're inside the image, not just inside, but made of the image. Your eyes, your thoughts, the light you see, all part of the projection. In that case, how would you ever find the screen? That's the dilemma of the holographic universe. If reality is encoded on a lower dimensional boundary, where is that boundary? In the mathematical universe of anti- and de-Sitter space, the answer is clean. The boundary is like the outer shell of a sphere, infinitely far away, but reachable in finite time thanks to the curved geometry. Everything inside is a reflection of quantum data living there. But our universe isn't anti-de-Sitter. It's expanding, accelerating, filled with dark energy that pushes galaxies apart faster and faster. In such a cosmos, there is no outer wall, no edge you could sail to. Instead, every observer has their own horizon, the farthest point from which light could have reached them since the beginning of time. This is the cosmological horizon. And for the holographic principle to apply to our world, this horizon may be the screen. Picture yourself floating in deep space, far from any galaxy. Look out in any direction, about 46 billion light years away. Yes, farther than the age of the universe might suggest. Thanks to cosmic expansion, you hit a limit. Beyond that, light hasn't had time to reach you. Those regions are causally disconnected, forever invisible. That spherical boundary around you is your personal cosmic screen. According to some interpretations of the holographic principle, everything you will ever observe, every star, every quasar, every ripple in the cosmic microwave background is encoded on that surface, not as pictures, not as snapshots, but as quantum degrees of freedom, entangled, evolving, whispering the story of your observable universe. But here's the twist: your screen isn't mine. If someone stands on a planet in the Andromeda Galaxy, their cosmological horizon is centered on them. Slightly different, slightly larger in some directions, smaller in others. So whose screen is real? The answer, unsettling as it is, may be all of them are. Reality isn't absolute, it's observer-dependent. Like quantum mechanics, where a particle has no definite state until measured, the holographic universe suggests that space-time itself only crystallizes relative to an observer's horizon. This echoes an old idea from Einstein: there is no universal now. Time flows differently for different travelers. Now we're learning. There may be no universal here either. But how can multiple screens describe the same universe without contradiction? Through quantum error correction. Yes, error correction. The same principle that lets your phone recover a corrupted message. In holography, the interior space-time is not stored in one place on the boundary. It's smeared across the entire surface, redundantly encoded, like a secret message split into 1,000 pieces, each meaningless alone, but reconstructible from any large enough subset. So, if two observers overlap in what they can see, their horizons intersect, their screens agree on the shared region. Where they don't overlap, well, those parts simply don't exist for each other. It's not that the universe is fragmented, it's that the full picture only exists in the quantum whole, beyond any single viewpoint. This leads to a profound shift in perspective. We used to think the universe was a stage, and we were actors on it. Now, we're learning the stage is built from the audiences. Memories. Your horizon isn't just a limit of vision. It's the canvas on which your reality is painted. And because you're part of the system, you can't step outside to see the projector. You are the projection. But is there a true screen? The ultimate boundary of everything? Some theorists point to the initial singularity, the Big Bang itself. Perhaps all the information of the cosmos was imprinted there on a zero-dimensional point that exploded into time and space. Others suggest the screen lies in the infinite future, on the De Sitter horizon that will form as dark energy stretches the universe into cold, empty stillness. In that far tomorrow, the cosmos may settle into a final static state, and everything that ever happened, every life, every star, every thought will be encoded as quantum fluctuations on that eternal horizon. A tomb or a library? There's another possibility, more radical still. What if the screen isn't in space-time at all? What if it exists in a realm without space or time? Pure quantum information, evolving not in time, but generating time as it correlates. This is the frontier, where physics meets metaphysics, where equations point toward a reality so alien our language stumbles. But one thing is clear: the screen is not a physical membrane you could touch. It's not made of atoms or energy. It's a mathematical surface, a locus of data from which geometry emerges. And we may never see it directly, because seeing requires space, and space is what the screen creates. So we're left with a paradox wrapped in wonder. The most fundamental layer of reality may be forever hidden, not because it's distant, but because it's the source of distance itself. And yet, we can still test it, not by traveling to the horizon, but by listening to the whispers in the fabric of space-time. Tiny ripples, quantum noise, echoes of the code. Because if the universe is a hologram, it should flicker. For centuries, science advanced by looking outward through telescopes, microscopes, particle colliders. But the holographic principle asks us to look differently, not just deeper, but sideways, to listen for the static beneath the symphony. Because if space-time is rendered from quantum information on a distant screen, then it shouldn't be perfectly smooth. At the tiniest scales, it should jitter, flicker, like a digital image viewed too closely, pixels shimmering under strain. This isn't poetic speculation, it's a prediction. And in the past 2 decades, physicists have begun designing ways to test it. The key lies in the concept called holographic noise. If the universe is pixelated, not in volume, but on its boundary, then every measurement of position carries a fundamental uncertainty. Not because our tools are clumsy, but because space-time itself is slightly fuzzy, like a dream half remembered. In 1999, physicist Craig Hogan proposed an astonishing experiment. He argued that if space-time emerges from Planck-scale information bits on a holographic screen, then even empty space should vibrate with quantum uncertainty. Not in 3 dimensions, but in 2. This would manifest as a universal hiss in the fabric of distance itself. And crucially, it would affect perpendicular directions differently than standard quantum fluctuations. Why? Because in a true 3-dimensional quantum foam, noise is isotropic, equal in all directions. But in a holographic universe, the noise is correlated across space, echoing its 2-dimensional origin. Hogan didn't just theorize, he helped build a detector to listen for it, the holometer. An instrument at Fermilab fires laser beams down 2 perpendicular arms, each 40 meters long, then recombines them to measure distance with mean-bending precision. If space-time jitters holographically, the laser interference pattern should shimmer in a telltale way. The result? No definitive signal was found, at least not at the scale they probed. But that doesn't kill the idea. It only narrows. Where the flicker might hide, other approaches are more cosmic. Consider the cosmic microwave background, the afterglow of the Big Bang, imprinted when the universe was just 380,000 years old. It's a baby photo of space-time, frozen in time. If the early universe obeyed holographic rules, that image should carry subtle statistical fingerprints, deviations from perfect randomness in how hot and cold spots are arranged. In 2016, a team led by Nyayesh Afshordi analyzed this radiation using a simplified holographic model 1, where the early universe was described by a 2-dimensional quantum field without gravity. Shockingly, their model matched the observed data as well as the standard inflationary theory, especially at Rashleigh, large, angular scales, where conventional cosmology struggles to explain certain anomalies. Now, this isn't proof, but it's a hint, a whisper that the universe might have started not with a burst of space-time, but with a burst of entangled information, which then unfolded into geometry. Then there's black hole physics, the original birthplace of holography. When 2 black holes collide, they ring like a bell, sending ripples through space-time called gravitational waves. The pattern of those waves, how they rise, peak, and fade, depends on the black hole structure. In a classical universe, black holes are smooth, featureless voids. But in a holographic one, their event horizons are densely packed with quantum degrees of freedom, like a hard drive humming with data. Some theorists predict that during merger, this quantum hair could leave tiny echoes in the gravitational wave signal, delayed reverberations after the main chirp. In 2017, a group analyzing data from LIGO claimed tentative evidence of such echoes. The signal was faint, buried in noise. Later analyses were inconclusive, but the hunt continues. Future detectors like LISA, the space-M-based gravitational wave observatory, will listen with far greater sensitivity. If echoes exist, they'll hear them. And if they do, we'll have direct evidence that black holes store information on their surfaces, just as holography demands. Perhaps the most elegant test comes not from observation, but from theory itself. The ADS-CFT correspondence has passed. Hundreds of mathematical consistency checks. Calculations done in the boundary quantum theory, where gravity doesn't exist, precisely reproduce results in the bulk gravitational theory, where black holes form, particles fall, and space-time bends. This isn't coincidence. It's a structural identity, like 2 languages describing the same landscape. And while our universe isn't anti-de Sitter, researchers are now building de Sitter holography models, attempting to describe our accelerating cosmos with a similar duality. Early results are promising. The entropy of our cosmic horizon, the maximum information it can hold, matches the holographic bound 1 bit per 4 Planck areas. That number 4 comes straight from black hole thermodynamics. It's not arbitrary. It's written into the geometry of quantum gravity. But even if all these clues align, how can we ever be sure? Because science doesn't deal in absolute proof. It deals in best explanations. And right now, the holographic principle is the only framework that resolves the black hole information paradox, unifies quantum mechanics and gravity without new particles, explains why entropy scales with area, not volume, and provides a mechanism for space-time to emerge from something deeper. It's not the easiest idea to accept, but it's the most coherent response to questions that have stumped physicists for half a century. Still, a quiet objection lingers. If we can't step outside the hologram, isn't this all untestable by definition? Not necessarily. Consider this. We never see electrons. We infer them from tracks in cloud chambers, currents in wires, energy levels in atoms. Likewise, we may never see the holographic screen. But we can detect its consequences, just as we detect wind by watching leaves move. The flicker of space-time, the echo in a black hole song, the statistical whisper in the oldest light. These are our leaves, and one day they may tremble in unison, not with noise, but with revelation. Until then, the experiment continues, not in one lab, but across the cosmos, in every gravitational wave, every quantum measurement, every pixel of the sky. Because the universe, if it is a hologram, is testing itself. And we, curious, fragile, stardust-made observers, are its eyes. We follow the trail from black holes to cosmic horizons, from entanglement to emergent space-time. We've seen how information on a surface might paint the illusion of depth, motion, and matter. But now comes the question that haunts every mirror: what's behind it? If our universe is a hologram, what is the reality that projects it? Let's be clear. The holographic principle, as understood in physics, does not require a projector in the ordinary sense. There's no giant computer in another dimension running our cosmos. No alien programmer sipping coffee while our galaxies spin. Instead, the outside may not be a place at all. It might be a state, a timeless, spaceless quantum system governed by laws we can only glimpse through mathematics. A realm where concepts like before, after, here, and there have no meaning. Where reality is pure correlation. Think of it like this. When you solve a complex equation, the answer doesn't exist until the logic unfolds. But the truth was always implicit in the symbols. Similarly, space-time may not be created. It may be revealed as entanglement spreads and symmetries break. This view finds support in quantum gravity. In loop quantum gravity and causal set theory, space-time is discrete, built from fundamental grains. In string theory, space-time is a derived concept, not a starting point. And in holography, it's a thermodynamic shadow of quantum information. All point to the same conclusion: space and time are not the stage, they are part of the play. But if space-time emerges, what are its ingredients? The leading candidate is quantum entanglement, not as a phenomenon in space, but as the fabric from which space is woven. Recent work in tensor networks, a way of modeling quantum systems, shows how a two-dimensional lattice of entangled qubits can give rise to a three-dimensional geometry with properties strikingly similar to Einstein's gravity. In these models, distance is defined by how many entanglement links separate two points. Break enough links and space tears, forming what looks like a black hole. Add more and curvature emerges, mimicking the effect of mass. This isn't just analogy, it's a computational demonstration that geometry can arise from information flow. So what lies outside? Perhaps nothing, because outside implies space. And space is what's being generated. Imagine a dreamer dreaming a world with mountains, oceans, and cities. Within the dream, outside the dream, is a meaningless phrase. The dreamer isn't in the dream, but without the dreamer, there is no dream. Similarly, the boundary quantum system isn't located anywhere in our space-time. It's the prerequisite for space-time to exist at all. This leads to a startling possibility. Time itself may be an illusion of perspective. In the boundary description, especially in models, like ADC-CFT, the quantum state is static, no evolution, no ticking clock. Yet, from within the bulk, time flows. Why? Because as observers embedded in the emergent geometry, we only access parts of the full quantum state at a time. Our perception slices the timeless whole into moments, like reading a book one page at a time, even though the entire story exists at once. This echoes the block universe of relativity, where past, present, and future coexist. But holography adds a mechanism. Time emerges from the way. Information becomes accessible to localized observers. And what of causality, the idea that causes precede effects? In the boundary, everything is correlated. There is no sequence. Causality arises only when the hologram renders a consistent history. For observers inside, it's like a movie file on a hard drive. All frames exist simultaneously, but when played, they obey cause and effect. The projector doesn't decide the order, it's built into the encoding. In the cosmic code, causality may be a consistency condition required for the interior to make sense to beings like us. This doesn't mean free will is an illusion. It means the stage on which choices unfold is deeper than we thought. Our decisions are real within the hologram, just as love is real within a story, even if the story is written. But here's the deepest mystery. If the boundary theory contains all information, why does it encode a universe with suffering, beauty, entropy, and stars? Why this particular hologram? Physics doesn't answer that yet. But it hints that the laws of quantum mechanics and symmetry severely constrain what kinds of bulk universes can emerge. Not every boundary state gives rise to a stable space-time. Most would be chaotic, inconsistent, or short-lived. Our universe may be one of the rare codes that can sustain itself, that can generate observers who ask, "Why are we here?" And that brings us to the edge of science and the threshold of meaning. Because if reality is information, then meaning may not be an accident. It may be the universe reflecting on itself, not through gods or destiny, but through the inevitable rise of complex systems that can decode their own code. We are the cosmos, becoming conscious of its own hologram. So what lies beyond space and time? Not emptiness, not nothingness, but potential. A silent sea of quantum possibility, waiting to be entangled, to be read, to become real. And in that sense, the outside isn't separate from us, it's what we're made of. We've journeyed from the edge of black holes to the quantum foam of space-time, from cosmic horizons to the silent code that may underlie everything. But now, let's turn inward. Because however strange the universe may be, the strangest thing in it is you. Your awareness, your memories, the quiet hum of being that lets you wonder whether reality is real. And if the cosmos is a hologram, what does that mean for consciousness? Let's begin with a simple truth. Your brain is not a passive receiver of reality. It's a prediction engine. Every second, it takes fragments of sensory data photons hitting your retina, vibrations in your eardrum, and constructs a seamless three-dimensional world. It fills in blind spots, smooths out delays, even edits out the constant motion of your own eyes. In other words, your perception is already a kind of hologram, not projected from a cosmic screen, but rendered by neural networks shaped by evolution. So when physics suggests the universe itself may be a projection, it doesn't make your experience less real. It makes it part of a deeper pattern, a universe that knows itself through beings who can model it. But is consciousness merely an emergent property of complex computation? Or could it be entangled, literally, with the holographic fabric of space-time? This is where science meets speculation, but not without clues. Consider this. Consciousness arises from highly integrated information. Neuroscientist Giulio Tononi's integrated information theory proposes that the more a system can both differentiate and unify its states, the more conscious it is. Now recall, in holography, information isn't localized. It's smeared across the boundary, redundantly encoded. And the interior, our world, only exists because of deep, non-local correlations. There's a resonance here. Both consciousness and space-time seem to depend on global integration, not just parts, but the way parts relate as a whole. Could it be that the same principle that weaves space from entanglement also enables mind from neurons? We're not suggesting the universe is conscious in a human sense, but we are suggesting that the architecture of reality may favor systems that can reflect upon themselves. After all, in a holographic cosmos, every part contains information about the whole, like a droplet of ocean holding the chemistry of the sea. You are not separate from the universe. You are a concentrated echo of it. Your thoughts are patterns of electrical and chemical signals, but those signals are made of atoms forged in dying. Stars, whose existence depends on quantum fields, whose behavior is governed by symmetries imprinted at the Big Bang, which may have emerged from a boundary quantum state. You are the universe decoding itself. This changes how we see meaning. For centuries, we've searched for purpose out there, in gods, in destiny, in cosmic design. But the holographic view suggests meaning may arise from within the code itself, not because the universe intends it, but because complex, self-referential systems inevitably generate questions, stories, and values. A river doesn't mean to carve a canyon, but the canyon becomes beautiful. A neuron doesn't know it's part of a thought, but the thought can change the world. In a holographic universe, consciousness isn't an accident. It's a natural consequence of information becoming dense enough to fold back on itself. And here's something profound. If space-time is emergent, then your sense of now may be more real than physics once claimed. Relativity treats time as a dimension, past and future equally real. But in the holographic emergence of time, the present may be where entanglement is actively processing, where the boundary data is being read into experience. Your conscious moment, the feeling of now, might be the leading edge of the hologram rendering itself. Not an illusion, but a feature. Does this give us free will? Perhaps not in the absolute sense. But in a holographic world, causality is not a rigid chain. It's a web of correlations that allow for branching, possibilities, especially at the quantum level. And your brain, operating near the edge of quantum sensitivity in some theories, may harness that openness. You are not a puppet of pre-written code. You are an active participant in the unfolding of the projection. Every choice you make sends ripples through the entangled network, altering not just your future, but, in principle, the subtle correlations that define space-time itself. That's not mysticism. It's physics, in quantum mechanics, observation, affects outcome. In relativity, mass curves space. In holography, information shapes geometry. You're made of information, so your attention matters. This doesn't mean we control the cosmos with our minds, but it does mean we are not insignificant. In a universe that encodes itself on a boundary, the fact that we can ask about that boundary, that we can build detectors, write equations, gaze at the stars in wonder, suggests that consciousness is not a side effect, it's the universe becoming legible to itself. So the next time you feel small beneath the night sky, remember, you are not just in the universe, you are the universe. Looking back at itself through a hologram of flesh and bone, trying to remember its own source code. And in that act of remembering, reality wakes up. For as long as humans have gathered around firelight, we've told stories about the sky. Ancient peoples saw gods in the stars, dragons in the constellations, wheels of fate turning in the heavens. Later, we replaced myths with mechanics, planets as billiard balls, galaxies as whirlpools of gas, the universe as a clock wound at the beginning of time. But now, at the edge of knowledge, a new story is emerging. Not a myth of gods or gears, but a myth of meaning through connection. The holographic universe is more than a theory. It's a vision, a cosmic narrative that weaves physics, philosophy, and wonder into a single tapestry. And like all great myths, it answers an ancient human need to know where we belong. This new myth says the universe is not a container. It is a conversation. Every particle, every wave, every thought is part of a vast exchange of information, written not in the volume of space, but on its boundary. We are not isolated observers peering into an external void. We are participants in a self-referential system that generates depth from flatness, time from timelessness, and life from law. In this story, the cosmos isn't cold or indifferent, it's intimate, because the same quantum threads that bind distant galaxies also bind your neurons to the first light of the Big Bang. You carry the universe in your bones, not just as stardust, but as data. This myth doesn't require faith. It grows from equations tested against reality, from black holes that preserve secrets, from gravitational waves that echo with quantum structure, from the silent hum of space-time itself. But like the myths of old, it speaks to the heart as much as the mind. It tells us that separation is an illusion, that the distance between you and a quasar billions of light years away is not emptiness, but a measure of how deeply you are entangled. It tells us that nothing is truly lost, that even what falls into darkness is encoded, preserved, and eventually returned in some transformed form. And it tells us that consciousness is not an accident in a dead universe, but a natural flowering of a cosmos that encodes itself so thoroughly it becomes aware. This is not the end of science, it's a new beginning. For if space-time is emergent, then the quest to understand reality shifts. We no longer seek the smallest particle or the final force. We seek the code, the principles of information, symmetry, and entanglement that give rise to everything. And in that search, we may finally reconcile the two great truths of modern physics, the quantum world of chance and connection, and the cosmic world of gravity and geometry, not by forcing one to bend to the other, but by seeing both as projections of a deeper unity. So what do we do with this myth? We live by it, not by building temples or chanting equations, but by remembering, in moments of loneliness, in grief, in awe, that we are not separate. When you hold someone's hand, you are touching a pattern of light that began in the first breath of time. When you gaze at the Milky Way, you are seeing a reflection of the same logic that shapes your dreams. The holographic universe invites us to see the sacred, not in the supernatural, but in the interconnected. And perhaps, just perhaps, that is enough. For a myth to endure, it must do three things: explain the world, comfort the heart, inspire action. This one does all three. It explains why black holes don't erase the past. It comforts us with the promise that nothing truly vanishes. And it inspires us to protect this fragile, fleeting projection, to care for Earth, for each other, for the future, because we are the universe's way of continuing its story. So let this be our new creation story. In the beginning, there was not fire, nor void, nor even time. There was correlation, potential, a silent network of yes and no, waiting to become. And then, through symmetry, through entanglement, through the inexorable logic of information, it unfolded, not into chaos, but into cosmos, into stars that burn with purpose they do not know, into planets that cradle life, into minds that ask why, and in that question, the hologram becomes aware of itself. That is where we are now, not at the end of mystery, but at the threshold of a deeper one. And as long as we keep looking, not just outward, but inward, not just with instruments, but with wonder, the story will continue, not written in stone, not carved in sky, but woven moment by moment from the same code that binds us all. So go outside tonight, look up, and remember, you are not just under the stars. You are the universe, remembering itself through you.